Are there specific architectural choices you have to make when designing a scalable system?
Let me maybe jump in on that one. It's hard to prove this, but we're talking about efficiencies. And if you can use the architecture to make the system more efficient, I kind of hinted earlier to compress a circuit so that you can, so that the system can run long enough to do something useful. That you could argue that's architectural. You can take advantage of, for instance, in our system we have very high connectivity. That is, we can do an operation between any pair of quantum bits in the system, even to scale. I think the one architectural feature that I think will be necessary in quantum computing is modularity, being able to stamp out small module quantum computers and hooking them up together. And once you do that, and again, this is nothing new. I think any complex system has modularity. I don't know, look at the airline hub system in the world. You know, an airline doesn't fly between every pair of cities. They have hubs to save costs on maintenance and so forth. And I think quantum computers will, of course, the bigger the system, the more open it is to having errors being observed by the environment. So by making it smaller, but somehow allowing connections that maybe you don't use so much because you're limiting connectivity by doing this, but at least you can still scale. So I think that's an architecture that will probably find its way into algorithms. Because when you look at an algorithm, you'll notice, oh, look, only this 10% of qubits are doing a lot of work. Let's make that one module. So that's a black art on how you tie a particular algorithm application to the hardware, to the architecture itself. And I think we're going to be absolutely reliant on that in the early years of quantum computing. Until qubits are a commodity and cheap, we're going to have to co-design the algorithms and the architecture with the hardware we have at hand. And only by doing that will we be able to get to a point where qubits and gates are a commodity and you can just scale at will. Sort of like we take 20 megabyte pictures on our phones every day. I mean, that's a total waste. We do it because, of course, memory is cheap. The silicon behind it is incredibly high yield and it works great. So we're not there yet, but architecture is going to, I think, play a huge role. And I'm not an expert in this field. You should ask somebody like Joe, who knows much more about architecture, quantum computer architecture than I do. But I do realize, as a hardware provider, we can't be ignorant of hardware, of architecture. And people inventing algorithms, they cannot be ignorant of the hardware. You really have to have this vertical flow between the people at the very top that might not care about silicon or atomic physics, and people like me at the very bottom that normally might not care about what's above the API.
So actually, if I could jump in with a question, I wanted to ask Chris and John, what do you see as the role of modularity? Do you see the effort to build a quantum computer, 5, 10 years from now, as focusing on monolithic processors as we are effectively today? Or do you see there becoming more specialized parts of a system? So at the moment, most systems tend to treat all qubits equally. But if you look at a modern computer processor, you have a modern computer system, you have different systems for storage, then for processing. You also have specialized parts of a processor for arithmetic or different tasks that require different connectivity. How do you see the technology evolving, say, over the next 10 years?
Yeah, I mean, I think it's a really interesting point, and yeah, absolutely, we change our information between magnetic domains to charge and semiconductor to photons down a fiber, without even thinking about it, in conventional computing, and certainly in the future, maybe 10 years, maybe beyond, in a mature quantum information industry. Certainly, one could envisage that sort of fluid transfer of quantum information. But I I'd like to stress, some people think we're in the kind of 1980s era of quantum computing. I think we're more in the sort of 1950s era of quantum computing, where you had, valve computers and mercury delay lines. Anyway, I wasn't there, but I've heard about these things.
I think it's
you
like
know,
1947 or 1948.
okay, yeah. So,
if we're in the 50s, that's doing well.
Yeah. So, I think all of that we can see is to come, but really now, I think that the for developing the sort of first useful quantum computing applications, I don't see that really as a problem that's going to be solved by using quantum memory and these kinds of things, perhaps. And it's really about taking some of these systems and optimizing them as well as we can. I mean, the modularity is an interesting point. I can see some advantages. That to go back to the jet engine example, that's not modular, right? You kind of build a jet engine. Of course, you can strap a few of them together and make the plane go faster, and you can do that with separate quantum processors without having to make them modular in a quantum sense. So it can help with scaling, but there are very many extremely complex systems, including computing systems, which aren't don't necessarily have that modularity. And so I think it's not a fundamental requirement for quantum computing. There are different ways that you can enable that sort of scaling.
So in the context of something like an ion trap, this doesn't necessarily mean that you would have multiple different technologies connected together, an ion trap to superconducting qubits or something like that. But it might be as simple as multiple species in a trap. I say as simple, realizing that this is not simple at all. But I'm just wondering, I guess, Chris, what your thoughts are in terms of, if we're moving towards things like segmented traps, you can think of perhaps different trap regions for different functionality, and how that kind of thing goes into your thinking, or whether it doesn't at all, and it's better to avoid those complexities.
Oh yes, we of course think about that sort of phase one of the scale up is to we deal with a single core, we call it, of up to maybe 32 or so qubits, and they just sit there, they never move. We have a bunch of laser beams that poke at them, and we have full connectivity between all those 32. And of course, with 32 of anything, there are something like 500 pairs or something. So we can do any of 500 two-bit operations here. Now, to get well over 100 qubits, we think about having multiple cores on a single chip, like the one behind me, where we actually move atoms between them. Now, when you do that, you are limiting connectivity. We can only sort of hit the end ions. The end qubits go back and forth, and that should get us maybe to 1,000 or a few thousand qubits on a single chip. But then the launch to this modular photonic interconnection allows us to go off chip to another chip, and you might think that limits connectivity as well, but actually no. We retain full connectivity because each chip has one or more fiber lines that comes out, and they all go into a cross connect switch, and end by end cross connect switch. So picture the old telephone operator that's taking any input fiber and matching with the output fiber. We can match any pair of chips. So maybe we have 1,000 chips all on a single rack mount like a data center, and we have full connectivity between any qubit in the entire system. So in our platform, that's the natural way to scale. And you mentioned, okay, so there's shuttling. We need multiple species because when you shuttle, that causes heat. In a sense, you have to quench that. We also need multiple species to make the photon, because making the photon is a process that you can't have even a single photon hit the memory nearby. So we have communication qubits and memory qubits. So this has been done. All these demonstrations have been done over the last decade in university labs mostly, but at INQ we're doing all that stuff. But I would say that when you say different systems, I mean the photonic qubit is something we actually don't use in a single core quantum processing unit, but it is a quantum system that has the advantage of being able to go through fibers at room temperature without loss over small distances. So that system we're definitely going to juxtapose with our atoms. Going all the way to solid state, there's wonderful research on doing silicon optically active interfaces. superconductors can be made into a microwave cavity that has a mechanical mirror that moves, and you can, this is all researchy. The fidelities are very low. It's wonderful research, and eventually, I think there are ways to optically link even superconducting qubits. But I think we're a long way away before these different technologies will make one big processor.
Yeah, there's some really interesting work from Andreas Walraff on superconducting qubits, where they've made this giant tunnel between two dilution refrigerators, which was not the way I was expecting two chips in different
They're optical
pilfrages.
fiber. They're optical fibers this big, and it's near 0 Kelvin.